everybody, it's Mrs. Hofferberth. Let's talk about the concentration of solutions. First, let's make sure you guys are clear on what a solution is. And the solutions we're talking about here are aqueous solutions. So if you recall, if something is aqueous, that means it's dissolved in water. So what we're talking about here is taking a chemical, be it an element or a compound, and adding it to water and having it dissolve into that water. The chemical that you're adding, well, again, that element, that compound, whatever it is, the chemical that you add, and so typically is there in smaller quantity, that's called your solute. Well, the solvent is what's actually doing the dissolving, and in our case, it's going to be water. So I know you played with a sim the other day, but let's take a look at the sim that you were using. So this is the PhET concentration sim, and you played with adding a variety of different solutes to the water that was in the container. And so as you add the solute, you see it starts to dissolve and you see the color change when those particles spread out throughout the water. And the solute is the chemical that we're adding and the solvent was the water. And so we're talking about solutions, and these are going to be homogeneous mixtures. We're going to assume that our solvent completely dissolves and equally distributes whatever solute we are adding. Now, when it comes time to talk about the concentration of the solution that we're making, we know that that depends on two things, and this is what you would have played with the sim the other day. It depends on how much of the solute we add. The more we add, the more concentrated the solution is going to become. On the sim, we see this in two places. We see the solution become a darker color to represent that greatest concentration, and the concentration meter over here is increasing as this becomes more concentrated. And so what concentration is it's the ratio of how much solute do you have divided by how much solvent, or better yet, how much of the solution you have in total. And so if you were to increase the amount of solute, this numerator would increase because concentration and the amount of solute, or the moles of the solute, are directly proportional. On the other hand, if you were to increase the amount of water that was present in this solution, now we have a greater total volume of solution, and since volume is in the denominator, we're dividing by a larger value and we'll get a smaller answer. And so the concentration depends on both the amount of solute that we have present and the total volume of solution. And so pictorially, if I wanted to draw kind of a particle visualization of what's going on, when I add a small amount of the solute, we'll have a few particles. And while these might have been clumped together in the solid, when they dissolve into the water, they're going to spread out. If I add more solute to the same amount of solvent, you'll see that there's a lot more particles per volume. The more concentrated something is, the more closely packed those particles are going to be, the more particles there are per liter of solution. On the other hand, if I start adding more water to this, then I'm going to have the same number of particles, but they can be spread out over a larger volume, which decreases my concentration. They'll be more spread out. There's also one other situation that I want to point out. So far, we have taken our container and I've added more solute, and then I've added more water. If I was to continue to add more and more and more solute, at some point, you start adding so much solute to this solution that it can't dissolve anymore. In order for the solute to dissolve, it has to be able to interact with the water, and at some point, it just goes beyond what the water can manage, and you'll start finding that any additional solute that you add just collects on the bottom of the beaker. It doesn't actually dissolve. And at this moment in time, it turns out that the concentration in the beaker stops changing. You have as much dissolved as you possibly can. And this is what we call a saturated solution. And a saturated solution has the maximum amount of solute dissolved. Any extra solute will not dissolve and will just remain on the bottom of your container. So qualitatively, we can talk about things becoming more concentrated, or things becoming more dilute. Dilute meaning less concentrated. And that's a qualitative measurement. We can also put numbers to this process. And this is where molarity comes into play. Molarity is a way of measuring the concentration of a solution. And the number that we come up with mathematically is found by taking the number of moles of your solute and dividing it by the liters of the total solution. So a capital M is the symbol for molarity. It is also the unit for molarity. So it's both a symbol in an equation and a unit. And then moles of solute, you know, you're familiar with moles, and liters of solution you're familiar with. Now, formally, this is the total volume of the solution, which is the liquid, the water, and the solid that we added. We're pretty much just going to ignore any volume that the solid would take up because typically it's much less than the total volume of the solution. So moles of solute divided by liters of solution. And this is just a really nice equation that we can use to calculate molarity. So for example, if we have 0.348 moles of copper 2 chloride and we're dissolving it in 650 milliliters of water, and we want to know the concentration of the resulting solution, I can plug these values into this equation. So again, molarity is moles over liters. But I'm going to notice something. In this problem, I have moles, but I was given milliliters, not liters, which means the first thing we're going to have to do is convert from milliliters to liters. You can do this using proportions. You can use it doing dimensional analysis, your choice. For this here, I'm going to do it in dimensional analysis. When you take a look at all of my keys, both in the practice problems here and moving forward, I'll have both dimensional analysis and proportions shown. The key thing about this conversion is to remember that there are 1,000 milliliters exactly in every 1 liter. This is an exact value and will not impact the significant figures in your problem. Once you've converted to liters, then you're going to use the molarity equation and plug your values in. So the moles here was 0.348. The liters is 0.650, and this gives us a molarity that is 0.535 molar in our copper 2 chloride. Let's take a look at a couple of the other types of problems that we can do involving this molarity equation. What's the concentration when I take 6.05 grams of iron 3 nitrate and dissolve it in 1.40 liters of solution? Remembering, since I'm asking for concentration, that is molarity. Molarity is moles over liters. Well, I see liters here, 1.40, but I don't see moles. In this case, first thing we're going to have to do is to convert grams of that iron nitrate to moles. Here I've worked the conversion in both proportions and dimensional analysis, and so you can, again, always choose the method that you prefer. The molar mass for iron nitrate from the periodic table is 241.88 grams. Once I've converted from grams to moles, then it is time to use the molarity equation. And you'll see that I get 0.0179 molar. It is important that you write the unit following the final value rather than just leaving it as big M equals 0.0179. The big M at the beginning, that's the symbol for molarity. The M after the number, that's the unit. So you do have to put it after the value as well. So here we've gone, again, calculated concentration, but in this case we had an extra step to do to go from grams to moles. It is also possible to go backward, to know your concentration in the first place, and to solve for the amount of a material needed, or the volume of a solution. Again, our focus and our key for this is going to be the molarity equation. But now I know big M to start with. I know the molarity. I know the volume because 550 milliliters is 0.550 liters. And so what's missing is the moles. So the first thing we're going to do is use the molarity equation. And we're going to solve for moles. So you'll see I've plugged in the value for big M, I've plugged in the value for liters, and I find that I need 0.0550 moles of the potassium chloride, which is KCl. At this point, I'm halfway there. The question asked for grams. And so the second thing I'm going to do is I'm going to convert from moles to grams using the molar mass of potassium chloride. Once again, I've worked that conversion both in proportions and in dimensional analysis, and either way you're going to get 3.73 grams of potassium chloride being necessary to dissolve in order to get the target concentration for that volume of solution. So in sum, from this video, I'm hoping you understand what concentration is and kind of have a particle visualization view of what happens in a more dilute or less concentrated solution versus a more concentrated solution. You should be able to use the molarity equation, big M, molarity equals moles over liters, to calculate the concentration of a solution given the volume and amount of solute, either in moles or grams, that you're starting with. You also should be able to work backward, given a concentration and a volume or a number of moles. You should be able to find the missing piece of information in order to predict how to make a particular solution.